We are diving straight into Wonder, Video World Model Done Better. This is a June 2026 paper from researchers Jikang Zhu, Yikan Mei, and their team at Adobe Research and Johns Hopkins.
Yeah, and the claims here are just massive for interactive AI.
Right, so here is the absolute core of what you need to know up front. Wonder is a real-time 16 frame per second video world model. It takes a single image or a source video and turns it into a navigable, minute-scale 3D or 4D playable environment.
Exactly, and it does this by solving that classic simulation trilemma, right?
Yeah.
Balancing real-time efficiency, accurate camera control, and long-term memory.
Which is huge. And they solved it through a system-level co-design with 3 major breakthroughs. First, a pixel space coordinate field for visual camera control. Second, a sparse attention memory system that basically keeps the full KV cache without slowing down the inference.
Yeah, zero latency penalty on that.
And third, this highly specialized distribution matching distillation pipeline. It uses a mixture of students and Jan control regularization to prevent camera drift.
It is a totally brilliant template for next-generation systems.
Absolutely. So welcome to AI Paper Slop. If you are watching this series, you are about to unpack the exact architectural tricks that make this model tick. We are getting into how you force a massive diffusion transformer to stream at real-time speeds without, completely breaking its brain.
Yeah, it's not easy. We should probably start with the baseline they built on top of.
Good call.
Yeah.
So the starting point for Wonder is 1.2.1 I2V14B. For those of you familiar with it, it's this incredibly powerful 14 billion parameter bidirectional video diffusion model.
Right, and it has a 3D causal VAE built in. But the overarching bottleneck in this field is just the bidirectional nature of these high-fidelity models.
Yeah, they're designed to compute fixed-length chunks in one single massive shot.
Exactly. So converting a giant like 1.2.1 into a causal autoregressive generator, one that streams out a few steps at a time for real-time play, it usually breaks things.
It breaks at least one of those 3 pillars we mentioned: controllability, memory, or the real-time latency itself.
Because the prior methods, they really only fix a subset of those problems. Like, if you use a sliding window for your context memory, your latency stays low.
But the model essentially gets amnesia. It forgets the past.
Right, lost-see memory. But then, if you try to fix that by using dense attention to remember every single generated frame, well, your compute latency just blows up exponentially as the sequence gets longer.
And if you try to steer it using abstract pose conditions, the camera just drifts all over the place over a long rollout.
Yeah, the latency issue is purely mathematical. Attending densely to all historical key value states in a standard transformer means your per-step compute cost scales quadratically.
Or linearly, if you use certain optimizations, but still.
Right, still terrible. You cannot maintain a minute-long simulation at 16 FPS if frame number 500 takes 10 times longer to compute than frame number 5.
Okay, I want you to imagine driving a car, right? But you're looking only through a tiny cardboard tube.
That sounds terrifying.
It is, but that is sliding window memory. You can drive fast, but you have no idea where you just came from. If you turn around, you are completely lost.
Yeah.
Now imagine trying to process a massive high-res panoramic photo of every place you have ever been before you're allowed to press the gas pedal for the next inch.
Right, that's dense attention.
Exactly. Neither works for real-time driving. So I have to ask, if 1.2.1 is already this massive 14 billion parameter beast, how on earth are they squeezing interactive real-time performance out of it?
Well, you have to completely redesign how the model understands camera motion. Like, to make it interactive, you first have to tell it how to move.
Which brings us to the first breakthrough.
Yeah. The existing methods for this are super flawed. Implicit methods, which are the most common, they take 6 degrees of freedom camera poses, project them into MLP or ropey embeddings, and just index them.
But those global numerical representations, they're so abstract.
Extremely abstract. They give very coarse cues, which causes that control drift you mentioned.
The model just loses the plot on what the raw math means for the actual pixels. But what about explicit methods? Because prior models, like in Spadio World, use point cloud re-rendering, right?
Yeah, explicit methods fix the geometric accuracy, but they fail spectacularly in unseen areas.
Because they rely on offline pose estimation.
Right. They build a 3D point cloud from the input image, then re-render it from the new viewpoint to condition the model. But if the camera turns around and looks at an area that wasn't in the starting image, what happens?
The model just sees an empty black void.
Exactly, total black screen. Plus, running those external reconstruction modules adds crazy latency.
So it's fundamentally not streamable,
Mhm.
which is where Wonder introduces the pixel space coordinate field.
This is such an elegant solution.
It really is. Instead of abstract math or heavy point clouds, they use a super lightweight OpenGL renderer. It runs at like 150 frames per second.
Basically for free.
Right, and it creates this synthetic 3D scaffold. It's a dense, brightly colored geometric lattice paired with a colored spherical environment map at infinity.
So they translate any arbitrary camera trajectory into dense, frame-aligned visual cues.
Like if the camera translates forward, the 3D grid on the screen deforms. That gives explicit parallax.
And when it rotates, the infinite background map changes, which gives orientation cues. Then these synthetic rendered frames are just encoded by the VAE and concatenated directly with the noisy scene latents.
It's like dropping a neon green motion capture grid and a painted skybox over a blank holodeck. You are giving the model a literal visual wireframe of the camera's motion.
Yeah, that's exactly what it is.
But I have to push back here. Does concatenating this synthetic neon grid with the actual photorealistic video latents confuse the model? I mean, you're feeding it literal garbage visual data right next to the real scene.
It sounds like it should fail, but it actually stabilizes the diffusion process way better than numerical embeddings.
How so?
Because diffusion models are visual engines, right? Their convolutional and attention layers are built for spatial, pixel-aligned information.
Ah, so you speak its language.
Precisely. By providing explicit visual semantics, the grid lines shifting with parallax, the model doesn't have to decode complex math. It just correlates the optical flow of the synthetic lattice with the optical flow of the generated scene.
And since that lattice is mathematically infinite, it never returns a black void when you turn around. The grid is always there to anchor it.
Exactly. Steerability solved.
But that introduces the next problem. If it can drive for a full minute and turn back around, it has to remember where it started. We need long-term memory, but we already said we can't blow up the GPU bandwidth with dense attention.
Right. Which brings us to breakthrough number 2. Instead of compressing historical frames, which destroys fidelity, Wonder keeps the entire historical KV cache in full fidelity.
Wait, didn't you just say that dense attention to a massive KV cache ruins the latency?
I did, but Wonder decouples memory storage from memory attention.
Okay, unpack that for me.
So the historical chunks store their full dense keys and values in memory. But to actually retrieve them, the model uses a very lightweight pooled key summary.
Let's talk about the math on that retrieval. Because at each step, the model selectively attends to a constant-sized set of chunks.
Right, regardless of how long the video gets.
It always grabs an attention sink, which is chunk 0, to ground everything.
Yeah.
It always grabs the most recent chunks. I think they set R to 2 for local motion smoothness.
Yep.
And then it grabs a top cup retrieve set from the middle history based on how similar the current query summary is to those historical key summaries.
And because you pool the keys, the dimensionality is so small that computing cosine similarity across thousands of historical tokens is mathematically trivial.
It's basically free to search the history.
Exactly. But once it selects those top keck chunks, it attends to them using their full resolution keys and values.
Yeah.
Since your top K budget is fixed, your active attention context stays constant. Second number 60 takes the exact same compute time as second number 5.
Okay, that fixes latency, but it creates a massive train test mismatch.
You mean the sparsity?
Yeah. If I train a massive diffusion model to expect total recall with dense attention to the whole sequence, and then at inference time I hand it sparse flashcards, shouldn't it hallucinate?
It absolutely would, which is why they co-designed the training with something called sparse context forcing.
What does that look like during training?
During the ODE initialization phase, the causal student is explicitly trained to expect that sparsity. They use a Bernoulli distribution to randomly drop eligible non-local historical edges.
So they're forcing the student to learn how to generate accurate frames while missing huge chunks of context.
Yeah, they preserve the anchors, the self-attention in the current frame, the first frame, the recent frames, but the rest of the history is randomly masked out.
That's brilliant. It can't rely on lazy, dense dependence. It has to learn robust retrieval from partial memory, which perfectly mirrors what it has to do at inference time.
Exactly. It's a complete system co-design.
Okay, so we have steering with the lattice, memory with sparse KV, but we still need raw speed. A 50-step diffusion process won't run at 16 FPS.
No, you have to distill it down.
Right, we have to compress a multi-step bidirectional teacher into a 4-step real-time student without it turning into, well, slop.
Which brings us to the Distribution matching distillation, or DMD baseline.
Yeah, standard DMD has major failure modes for world models. You get mode shrinkage, blurry details, and that massive camera drift.
Because asking one causal student network to approximate a many-step teacher in just 4 steps is a huge capacity bottleneck. The student just doesn't have the parameters to do structure, physics, and texture all at once.
So Wonder fixes this with a mixture of students, the MOS architecture. They use 3 distinct 14 billion parameter student generators for the 4-step sampling.
Right. G1 does step 1 for course structure, G2 does step 2 to refine it, and G3 handles steps 3 and 4 for high-frequency details.
Wait, loading 3 separate 14 billion parameter models sequentially at 16 FPS. How does that not fry the GPU or tank the frame rate?
It sounds impossible until you look at the memory architecture. The real bottleneck in autoregressive generation isn't loading weights, it's computing and passing the KV cache.
Oh, I see.
Yeah, in the MOS design, these 3 students share the exact same streaming autoregressive KV cache.
So G1, G2, and G3 aren't building separate temporal contexts.
Nope. They act as specialized, sequential denoising layers applied to a unified hidden state. G1 passes its hidden states directly to G2, updating the single cache in one linear flow.
It drastically increases parameter capacity without adding any memory overhead.
Exactly. But MOS only fixes the blurriness. To fix camera drift, they had to invent Jan control regularization.
Right, because standard DMD uses high-frequency score differences. It heavily weights sharp edges, but completely ignores low-frequency layout changes, like a camera panning left.
Yeah, if the student drifts off the path, standard DMD might just say, well, the wall texture looks realistic, so it's a good generation. It ignores that it didn't follow the lattice control.
So Wonder introduces a specific control discriminator. They take the student's rollout, add high noise, and pass it through the frozen bidirectional teacher.
And here's the genius part. They compare the intermediate features of the student rollout against the first layer features of the teacher.
Because the first layer is where that synthetic visual lattice actually gets injected into the model.
Yes. By checking if the internal representation still aligns with those raw first-layer camera instructions, they force strict adherence to the trajectory.
And they apply convolutional downsampling to these feature differences, right? Yeah. To create low-frequency maps.
Right. They force the discriminator to ignore the high-frequency pixel textures entirely and focus purely on spatial layout and camera motion consistency.
Unbelievable. Okay, so we steer with a synthetic grid, maintain memory with pooled key summaries, and is still using 3 specialized students policed by a low-frequency gen.
That is the architecture in a nutshell.
But an architecture that complex needs serious fuel, right? Let's dig into the data curation and systems engineering.
The data engine is super robust. For image to video, they mix real-world navigation data, like from DL3DV, with synthetic data from Unreal Engine.
Why do they need Unreal Engine data?
Because human camera operators are too smooth. Real-world data doesn't teach the model how to handle hard camera paths, like sharp lateral movements or sudden reversing.
So Unreal teaches it the extreme physics.
Exactly.
And for video to video, where you're changing the camera angle on a moving scene, they use Blender to render long, paired trajectories.
Yeah, they specifically include speed-varied sequences and bullet time videos.
Okay, I have to stop you there. Think about the matrix for a second. Why does an AI world model need bullet time synthetic data?
Because it mathematically decouples space and time. If a model only sees training videos where the camera and the subject move simultaneously, it conflates the two.
So if you pan the camera quickly, it accidentally speeds up the person walking.
Or freezes them entirely if the camera stops. Bullet time data forces the model to learn that spatial viewpoint changes are totally separate from temporal scene dynamics.
That makes so much sense. They also use depth anything 3 for precise pose estimation. And they apply Gaussian smoothing to the trajectories to remove jitter.
Right, because if your ground truth data vibrates, the model will vibrate.
Now, beyond the data, we have to talk about the hardware execution, because this is where a lot of ML engineers hit a wall. To actually get 16 FPS on a 14 billion parameter model, they compile the PyTorch ops, use flash attention 3 on Hopper GPUs, and heavily use sequence parallelism.
Yeah, sequence parallelism is non-negotiable here. When you have a massive streaming KV cache, if every GPU tries to hold the whole cache, your VRAM just instantly balloons and you crash.
So instead of duplicating the cache, they distribute it across the attention heads and the GPUs. Like GPU 1 takes heads 1 through 8, GPU 2 takes 9 through 16.
Exactly. Each GPU only processes its assigned subset. They compute their outputs locally, do a fast all-gather operation, and combine the results.
It slashes the memory bandwidth. It's really a masterclass in hardware-aware software design. So let's look at the results. Did this massive code design actually crush the benchmarks?
Definitive yes. On the vBench image-to-video metrics, Wonder scores an average of 408,558.
Beating out HY WorldPlay 1.5, Realiscy, and Santa WM.
Comfortably beating them? But the metric that really matters is the relative pose error, or RPE.
Right, how closely the generated camera path matches the requested path.
Wonder gets translational error down to 0.0132 and rotational down to 0.0784.
Which vastly outperforms models like in Spadio World, because those models rely on point cloud re-rendering, which fails in unseen territory.
Yeah, but the qualitative tests are my favorite part. They have this one evaluation where they command the camera to do a full 360-degree pan.
So it looks completely away from the starting room, explores a new space, and rotates all the way back.
Right. Other state-of-the-art models simply hallucinate an entirely new room when they get back.
But Wonder leverages that sparse memory, pulls the exact visual tokens of the starting room, and faithfully reproduces it.
Without tanking the frame rate, it actually remembers.
So for you ML engineers out there building these systems, the key takeaway is clear. To achieve real-time, minute-scale video world modeling, you cannot optimize your control, memory, and distillation in isolation.
No, if you hack memory for latency, you lose world coherence. If you hack distillation for control, you lose speed.
It has to be a coupled, system-level design, which leaves me with one final thread to pull on.
Let's hear it.
Wonder relies heavily on camera geometry, translating motion into that visual lattice. But what happens when we want to control non-camera physics?
Like object interaction.
Exactly. What if a user wants to push an object in the generated video? Could this pixel space coordinate field be adapted for that? Imagine a localized warping grid representing physical forces.
Oh, that's interesting.
Right. If you push a generated card, the grid deforms locally. If the diffusion transformer can follow a global moving grid for the camera, could it follow localized lattice perturbations to compute object velocity or even fluid dynamics?
Translating raw physics into visual lattice deformations.
It completely changes how we might build interactive game engines in the future. Something for you ML engineers to tinker with this week. Thank you for joining us for this deep dive on AI Paper Slop. We will catch you on the next one.